Okay, in this video I'd like to walk through 3 examples of calculating margins of error and a confidence interval when sigma is known, when our population standard deviation is known. And so in example 1, this problem is titled Pulse Rates of Females. For the sample of pulse rates of women, we have n equals 40, so this means we have a sample size of 40. There were 40 women in our observational study. And of those 40 women, the average pulse rate was 76.3. So again, X bar is the average statistic. This is the average based on the 40 women that we were able to observe. This sample is a simple random sample, so it's a random selection of all females in our population. Now we're going to assume that sigma is known and it is equal to 12.5. If we use a 0.95 confidence level, we can find the following: the margin of error and the confidence interval for mu, or the average pulse rate for the entire population. Well, the margin of error is easy enough to find. It's equal to the critical value, z sub alpha divided by 2, times our sigma divided by the square root of n. So we found in the last example that z sub alpha divided by 2, well, that's equal to 1.96 and negative 1.96. But let me again show you how we got to that. Our alpha value, or our confidence level, is 0.95, and that needs to be divided by 2. We're going to multiply that critical value times our sigma, which is 12.5, divided by the square root of 50. So again, if we're looking for a critical value here, 0.95 when divided by 2 is 0.475, and that critical value is going to be multiplied by 12.5 divided by the square root of 50. Whoops, and that's not right. I made a major mistake right there. Alpha is not the 0.95, it's not our confidence interval, it's the complement to our confidence interval. So this should have been 0.05 divided by 2, and that's 0.025. This is the area to the right or to the left of the tail that we're interested in, not in between the tails, but to the outside of the tails. Now, as I mentioned before, we can use our calculator to obtain this particular confidence interval, or this critical value. So I'll go to the calculator now and select menu 653, since we have an area and we're calculating our z-score, the critical value. 0.025 is the area. I'll leave mu and sigma alone right now, assuming that this is a standard normal curve. And we see that our z-score is negative 1.9599. We'll round that to 3 decimal places. Negative 1.96. Now that gives me the z-score on the left side of a standard normal curve. This is negative 1.96. We also have an equivalent number on the right side, 1.96. And that's why with our confidence interval, we'll use the plus or minus sign. And if you want to use that in your margin of error calculation, that's perfectly fine too. This needs to be multiplied by 12.5 divided by the square root of 50. And now we have an expression that we can go to our calculator with. Now our calculator doesn't have a plus or minus button, so I'll just use the positive calculation of this. 1.96 times a fraction of 12.5 divided by the square root of 50. And I just recognized something. I don't know why I've been using 50 this whole time, and actually should have been 40 here because we only had 40 women in our sample. So I need to make sure that I change that on our notes, and you should go back and check this too. But square root of 40 is what we're looking for in that denominator. And now we can press enter here. The upper margin of error is 3.874. So this is 3.874. And while I'm at it, I better correct this. These were all 40s here. We had 40 women in our population. Or, I'm sorry, in our sample, not our population. Okay, so that's my positive confidence interval. Margin of error, I should say. That's our positive margin of error. And we also have a negative version of that as well. Had I used the negative sign here, we would have had a margin of error at a negative 3.874. So what this tells us is that at whatever we find our average pulse rate to be within our sample, we would assume that with 95% confidence that the population's average would fall within 3.874 beats per minute, either above or below our sample. Now that's what part 2 refers to as our confidence interval. The confidence interval for mu is equal to our x bar plus or minus our margin of error. So in this case, we would expect with 95% confidence that our population average is 76.3 beats per minute plus or minus 3.874 beats per minute. Now, when I add 76.3 plus 3.874, I see that we have a limit of 80 beats per minute. And when I subtract 76.3 minus 3.874, I see that we have a low range of 72.426. Therefore, with 95% confidence, we would think that mu falls between 72.426 and 80.174. So that's our confidence interval, and this was our margin of error. Let's try another example. In this example, the salaries of college graduates who took a statistics course in college, let's suppose we're looking for a 95% confidence interval with a sample size of 41 individuals whose average salary was $67,000 to $67,200, and the standard deviation for the population is known to be 18,277. Let's find both of the following, the margin of error and the confidence interval. Well, the margin of error, again, is equal to z sub alpha divided by 2, our critical value, times sigma divided by the square root of n. And in this case, alpha is 5% because it's the complement of 95%. So we're looking for 0.05 divided by 2 times sigma divided by n. And we know that sigma is 18,277, and we're going to divide that by the square root of 41. And we don't actually have to use the calculator to recalculate this z-score. I know from the last example that it's a positive and negative 1.96. And that positive 1.96 can be multiplied by 18,277 divided by the square root of 41. So we can go to the calculator to find this result. Let's do the positive result first. So we have 1.96 times the division of 12,877. And nope, that's not right. 18,277 divided by the square root of 41. So our confidence interval is plus or minus $5,594.60. Now with that confidence interval, we can then answer part 2. I'm sorry, with that margin of error, we can calculate our confidence interval, part number 2. the confidence interval for mu in this case is equal to our x bar plus or minus our our margin of error. And in this case, our average was 67,200, 67,200 plus or minus $5,594.60. So this then comes out to be, let's go to our calculator and find this result. 67,200 plus 5594.6 and 67,200 minus 5594.6. So we have an upper limit of $72,794.60 and a lower limit of $61,605, $61,605.40. So what this means is that with 95% confidence, we think that the average salary for the entire population of students that took statistics in college will fall between $61,605 and $72,794. Let's try one more example, and I'll ask you to do this on your own and check your work. The only thing that I'll point out here is that we're working with a 99% confidence interval instead of 95. So you will need to use your calculator to find this alpha score, that critical value associated with the alpha score. So again, please pause the video now, try this work on your own, and resume playback in just a few moments to check your work. Okay, so in this example, the speeds of drivers ticketed in a 55 mile per hour zone with 99% confidence, and the number of tickets that we observed was 90, so that's the number in our sample. The average speed for those drivers in this sample was 66.2 miles per hour, and the standard deviation for all drivers that received tickets is 3.4 miles per hour. The margin of error, this time we used a alpha score of 0.01. That's the complement to 99%. So we had to use our menu 653 command, menu 653, to obtain the critical value that we got here, utilizing the area of 0.005 because that's half of 0.01. Now that critical value is a positive negative 2.56, with it multiplied by our standard deviation of 3.4 divided by the square root of the number of tickets in this particular sample, 90, we receive our margin of error of plus or minus 0.917 miles per hour. When utilizing that that margin of error, we now have a confidence interval to calculate. That average of 66.2 miles per hour plus or minus our margin of error indicates that with 99% confidence, we can say the average speed of all ticketed drivers is between 65.283 miles per hour and 67.117 miles per hour. Again, we don't know the average speed of all ticketed drivers. There are probably too many for us to calculate, but with 99% confidence, we can say that the average speed is going to be between 65.283 and 67.117 miles per hour inside this 55 miles per hour zone. So hopefully those examples help you out, understanding a little bit more about confidence intervals, and at the very least you have a method to calculate confidence intervals as well as margin of error on your own. We will see problems like this on the SLO, and we'll continue to practice them at least one more day before we start the SLO at the end of the week. Thanks.